In this video, we will be understanding Stern-Gerlach experiment. So this was first experiment that helped people visualize about how quantum spins work or what they are. And it also helps us in case of qubits understand that how a qubit, which is in superposition of state 0 and state 1, collapses into either ket 0 or ket 1 on measurement. So this is the apparatus of the experiment. We have two magnets and the south and north pole facing like so of the two magnets. Also, this south pole magnet is stronger than the other one. So what we can imagine is that if we take this magnetic dipole strip and pass it through this area and then let it fall behind on a screen, then this magnet of south pole is stronger. Therefore, north pole will be attracted towards it more and it will be deflected upwards, and that's where we will see it on the screen behind. If we were to invert this magnetic strip with the south pole above the north pole, then it will be deflected downwards because of the strong repulsive force from this south pole magnet. And if the orientation of this magnetic dipole strip were to be horizontal, then it will go straight and it will be undeflected. So what we can understand from here is that the orientation of the magnetic dipole strip matters, because that is what determines where it will land after getting deflected through these magnets on the screen behind. So this is what happens if the north pole is above, it gets attracted to the south pole and is deflected upwards. And if the south pole is vertically pointing towards the south pole, then it's get deflected because this upper magnet is stronger, and therefore the repulsion offered to the magnetic dipole strip is more. And if it's horizontal, then it just lands in the center. And then varying magnets can be projected like so at different orientations, and the possibility of them landing is somewhere on this vertical line depending on its orientation. Now, instead of a magnetic dipole, if we were to project an electron or some other quantum physical system that could represent a qubit, so if we were to project that through this experiment, then what we observe is that we only get two possibilities. Either the object gets deflected upwards or deflected downwards and nothing else, only these two options. So you could consider this as the first case in the magnetic example, wherein the north pole faces the south pole and therefore gets attracted. And this case wherein the south pole gets strongly repulsed by this south pole magnet and gets deflected downwards. And what we ultimately get is basically two spins, spin up and spin down, which is a good way of visualizing quantum spin, though we can't really see what their structure or properties are, but we can see what it means to have an upspin or a downspin. If it's up, it gets deflected upwards, otherwise downwards. So this experiment also helps us in understanding how measurement happens of a qubit. So if this is the experiment that we were seeing in the previous slide, so if this is a qubit, and qubit can be anything, an electron, any quantum physical system. And there are many ways in which we can make a qubit, but that's a topic for some other time. Let's just focus that these are qubits, and their spin is not necessarily up or down, it is anything. It can be anything, just like a qubit state. It can be in superposition of ket 0 and ket 1, and it can be in any state. But once it goes through this magnetic apparatus, then it either gets deflected upwards or downwards. So these two options, we represent it as the z-axis, where this is plus z or ket 0, and this is minus z or ket 1. So if the qubit that we project is collapsed and it measures to be ket 0, then it will get deflected upwards. And if its spin is that of ket 1, then it will get deflected downwards. And this is how we can measure a qubit in any given state, and it will collapse in either of these two states only, because these are the only possibilities that we get from Stern-Gerlach experiment. Now, we can also change the orientation of a magnetic apparatus. Instead of stacking them vertically, we can stack them horizontally, and we'll get something like this. The deflection will again be similar. It will either get deflected in one direction or the other, being only two options. And because it is horizontal now, so it won't be up and down, it won't be vertical, but our options will be left or right. This basis is known as the x basis, and if it's in minus x direction, then it's ket minus, and if it's in plus x direction, it's ket plus. So one interesting thing to notice over here is that if these qubits are ket 0 or ket 1, instead of being in superposition, and are projected through this magnetic apparatus, then it is 50% of the time they will go in this direction, and 50% of the time they will go in this direction. Therefore, we can also represent ket plus and ket minus in terms of ket 0 and ket 1. And how do we do that is something you'll see in the next video. Also, if this apparatus is rotated by 90 degrees, then we will get the y-axis, or instead of left or right, it will become forwards or backwards, and that will be our y-axis. So we have got 3 axes, and we can represent them like so in the form of a block sphere. So imagine if our qubits are coming from this direction, they can either get deflected upwards or downwards, that is ket 0 or ket 1 in case of z-axis. And if our apparatus is made horizontal, then our qubits will get deflected either left or right on this axis, which is the x-axis, giving us ket plus and ket minus as 2 options that we can measure. And if we rotate that apparatus by 90 degrees, we get the y-axis with these 2 options of measuring the output. This is our block sphere, though it looks 3D, but actually our possible states of the qubit are 2-dimensional, because ket 0 and ket 1 are 2-dimensional like we've seen before. So it is a way of really good way of representing a 2D information in form of a 3D sphere. This sphere is known as the block sphere, and it can represent any possible qubit state except for these 6. It can represent all the infinite possibilities, and they will be represented by points on the surface of the sphere. And more about block sphere is covered in the next video, so you can watch it. And if you're interested in knowing more about the details of Stern-Gerlach experiment, then there are a few links in the description, which are basically really good animations explaining the concept, and you can look at them as well. Thank you.